Alright, so moving on in statistics, we're on chapter 8, section 1, which is dealing with line fitting, residuals, and correlations. This whole chapter is dealing with um, creating regressions for different sets of data, and it's most specifically looking at our linear. Okay, so we're not going to be looking at like an exponential regression or a quadratic regression. We're going to specifically be looking at linear regressions that'll fit a line. Okay, so first thing, what a linear regression is. So a linear regression is used when we have some sort of a assumption that there's an association between two variables. And that assumption is that it's linear. So as one increases, the other one increases or decreases at a constant rate. Okay, linear objects would be something like every hour you work, you make $10. Okay, that would be linear. So if you work 1 hour, you get 10, 2 hours is 20, so on and so forth. Okay, so that's what we're looking for. So the equation here is y equals beta sub 0 plus beta sub 1 x, okay? And that is going to be our equation. And the betas, so those b's, b1 and b2, are our parameters, which are what we have to find, okay? And those will change based on whatever information we have. But the y, x, and the setup, how it's written, is the same. You can think of b1 as your slope and b0 as your y-intercept in a linear function. Okay. All right, so with a linear regression, we've got our two variables, the x and the y. We are going to be using, to describe these variables, we'll be using different terms for them. So an explanatory or a predictive or predictor is your x. So if you ever see him talking about explanatory, that's your x. And then your y is your response. Okay, it's your independent and dependent. Okay, the y relies on what the x is giving it to get its answer. That's why it's the response. Okay, and the x is what explains your answer. Okay, so that's for those. Okay, so with these, whenever we have these scatter plots, anything like that, we won't always have a perfect line that's going to be very easy to see. They're not all going to be in a row. They're going to be more of a cloud. And what we want to do is we want to find the line that fits that cloud the best. Okay, we want to see if there's a pattern. So you see, like with the first set of data down here, we have a bunch of points that are obviously decreasing as they move along the x-axis. And they're fairly close to that line, so they're kind of bunched together. When you look at the next one, the middle graph, you see that it's increasing, but they're farther apart. Okay, so it's not as strong of one. And then the last one, you see there's a whole bunch of points, but it just kind of looks like a cloud. And so that function would be kind of the weakest out of these, because there is because you can't really just see a pattern just by looking at that cloud of points. Okay. And you see it kind of is decreasing a little bit. Maybe it's perfectly horizontal, but it's still very difficult to see. Okay, so one thing you got to watch out for is that not all data will fit a line will fit in data. Okay, so if something is naturally curved, so this information is basically the angle in which you are shooting something. Like throwing something or launching something, and how far it goes based on the angle. So the angle's along the x-axis, and then the distance is along the y. So you see it peaks out at 45 degrees. So at 45 degrees, you would have the farthest distance thrown. But if you're shooting at 90 degrees or straight up and down, it's not going to go anywhere. So as you see, this is a parabola. It's a curved shape. This type of data you would not want to put a line on, because as you see, this line of best fit is a horizontal line, which doesn't really make sense. So if the data is straight or curved in any way, a straight line might not be the best. Okay, and we'll talk about that in more detail. Okay, so we have this graph here, which has the bushtail possums. It's the total length of it along the x and the head length along the y. Okay, and so you see this is showing one individual point, so it's like with the total length is about 89 centimeters, its head length would be about 94 millimeters, okay, around there. So that's what each of those points represent with this. So if we're looking at this, we could say that it's linear. So it looks like as the total length increases, the head length of these animals also increase, which kind of makes sense. If an animal's bigger, then it's going to have a larger body part, a larger head in this case. But it is fairly weak. It's not it's not all bunched together. Okay, if we draw a line, we would see like, oh, the line would be maybe about there. But as you see, they're not all bunched together. Okay, and so that's why we call it more of a weak linear. Okay, so again, watch out for curved relationships. So a straight regression a straight line regression is great for data that is a straight line. So like our possum information right here, which is showing this is kind of where the line should be, is somewhere in that darkened area. But if the data is curved in any way, so the miles per gallon and the weight of city driving for cars, you see as it gets larger, it kind of flattens out. So this wouldn't go all the way down and then you'd hit a point where if a car weighs so much you would have 0. This curves. So it's going to flatten out. We wouldn't want to do a linear for anything that flattens out or curves or has a peak in it and then falls back down. So we just have to watch out and make sure the data looks linear and would make sense for it to be linear before we start doing a regression, because it might not be the best for it. Okay, so up on top is the linear regression for the total length, head length of the possum. And that first y we would call y hat. Okay, and that's what we're going to use for our linear regressions. So our linear regressions will be denoted as y hat. Okay, if we want to estimate that the total length of the head length of a possum, if the total length is 40 centimeters, all we have to do is plug in the x. So we plug 80 in for x and solve it. So what would be the head length of a possum whose total length was 80? Right. So it would be about 88.2 millimeters. Okay. So again, all we do is we take this equation, which this is a predictive equation, and we just plug in whatever x or y value we want to find the other one. Okay. And again, it won't be perfect, because if you look here at about 80, we don't have any that are 80. And yeah, so around here, we don't have any that are about 80 centimeters. We didn't have any data points. So that means that what we're doing here is we're estimating what it would be. Now, if we do find one that's 80, it probably isn't going to be 88.2 exactly. It's going to be something close to it. All right. Okay, so next up is our residual. So our residual is the difference between the line of best fit and any data that we had. So, the one way of doing it is you take your fit and then you add whatever the residual is, and that's going to get your actual data points. Now that means every single actual data point that we collected, that we put into our regression, is going to have a residual. So that means if we had 100 data points that we threw in there, there would be 100 residuals to calculate. Okay. Another way of doing it is just doing the data fit minus, or the data minus the fit, and that gets you your residual. So you see you can get a positive or a negative number based on where the data falls. So that's how you find your residual. So the residual is the distance from the actual line to the actual data point. Okay. So every piece of data will have its own residual, so you have to calculate it. So if the data is above, so if a point is above the regression, would the residual be positive or negative, do you think? It would end up being positive. So if you have a line of best fit, and then you have a point up here, this distance would end up being positive, because it is above that line. So that residual would end up being positive. If you have a point that's below it, so down here, that would be a negative. Because if you remember, we take data point minus the line of best fit to get our residual. So if the data point is above the line, it's going to be a positive residual. If it's below, it's a negative. Okay, so looking at this graph, we have 3 points. We have an X, a cross, and a triangle. That's different than all the other ones. Okay, those dotted lines that you can see with them are our residuals. So that distance is the residual. Okay. If we want to talk about which residual is the largest, we want to make sure we take the absolute value of this. So if we were to rank these from largest residual to least or smallest residual, the largest residual would be this one, the cross, or the T. Okay, that would be our largest one. The next largest residual would be our triangle. Okay, and then our last one would be the X. So the X would be the closest to the line, which makes it the smallest residual. Whenever we're looking and trying to rank them from least to greatest, we have to take the absolute value of these numbers. Okay, so residual, this is kind of the formal way of saying it. So the residual of the observation, so whatever observation it is, 1 through 1,000 or whatever it is, which is the point, xy, is the difference between the observed y and the response y, based on the model, which is y hat. So the residual is going to be yi, or the data point I, minus the model fit I, which is y hat I. Okay. And again, we typically find y hat by just plugging in whatever the x is of that data point. So if I have, like if let's say my y hat is 3 plus 2x. Okay, just to make it simple, 3 plus 2x. And I have a point of 2, 3. Okay, so that's my point. If I want to find my residual, okay, it's going to end up being 3 minus, and then I have to calculate what y hat is, which I take this 2 and I plug it in. And when I take my 2 and I plug it in, I get 2 times 2 is 4 plus 3 is 7. So it'd be 3 minus 7, which makes my residual -4. So that means that that point is below the line, and it's 4 units below. Okay, so it's fairly large away from it. Okay, so that would be your residual for it. Okay, so if a model underestimates the observation, will the residual be positive or negative? So looking at this one, which points do you think would be underestimating, and would their residual be positive or negative? So if they're underestimating the observation, that means that the residual would be positive, because the point is, if the line is underestimating it, that means the point is above it. Okay, so that means the only one that would be that they're underestimating would be that T, or the plus sign. Okay, that's the only one that would be considered an underestimate out of the 3 red ones. Okay, so what about if they overestimate the observation? What's going to be true about the residual? In this case, the residual is going to be negative, okay, because we take our point minus the y hat, okay, which makes it positive. So if you overestimate, your residual is going to be negative. If you underestimate, the residual is going to be positive. Okay. All right, so after this, we have a residual plot. Okay, so a residual plot is a way to plot our data and look at it based on our linear equation. Okay, the horizontal axis stays the same. So if your original horizontal axis was the total length of the possum, that stays the same, and you want to keep it the same scale and everything, just so you have it constant. The vertical axis, though, is going to be the residual. So what is the residual of every point? Is it positive? Is it negative? How far away from it? And this is going to help us view our numbers. So here's our original graph that we had, and here's that line. So the next graph is going to show what the distance is to each of these points. Okay, that's a whole bunch of points, and it's going to show the distance. So the ones below are going to be negative, the ones above are going to be positive. And so this is what your residual graph looks like. Okay, That 0 would be our line of best fit. Okay, that's our regression that we have. And then as you see, all these points are above and below based on where that line is. So it's taken that line that was at an angle and flattened it out. And now we can see where all those points are. So now we can see which ones have large residuals, which ones have smaller residuals. Okay, this allows us to also help us identify if there's any outliers or if this data even is linear. Okay, which we'll talk about. Standard deviation of residuals is something that will be found. So basically you take all the residuals and then you do your standard deviation, like what we've talked about way back in the early chapters, doing those by hand, but you have your calculator. This is denoted by the letter S to find your standard deviation of the residual. It tells you the average error of it, but it's not finding the average. So you're not actually doing the average. Okay. So, and it's estimated from the residual plot. For the most part, if you don't have the data, so you just want to say, oh, I think it's about 2, I think it's about 3, if you have to eyeball it, okay, what the spread would be. And remember, with these, you want to fit into your empirical rule. So 68, 95, 99.7. So we want to go, okay, about how much above and below, which has to be equal, would about 68% of the data fall into, or 2 for 90 something. So if we go like 5, okay, so if we go plus or minus 5, you see that most of the data falls in there. I would state that probably about 95%, which means that we're 2 deviations. So that means that my standard deviation for this is probably going to be 2.5. Okay, so it's probably going to be about 2.5, and that's just a prediction. We'd have to actually find it using the numbers, but that would be kind of a prediction. So like what I've talked about here, again, north and south, that's about 2 deviations, and then I would, because it's about 95% of the data, so I'd say about 2.5. So about half that would be 1 deviation on either side. So I'd say it's about 2.5 would be the estimate. And again, you can go, well, no, I think it's probably more 2. I think it might be 2.3. We're splitting hairs here that we don't have to. We're estimating. We don't need it to be perfect. I feel justified with my explanation that 5 on either side would be good for 2 deviations. All right, so let's say we have these 3 residual plots on the left. So I'm going to label them A, B, C, A, B, C, and the other ones I'm going to label 1, 2, 3. Okay. I guess I should have put that one on the other side, huh? Make it kind of... Okay. So let's say I have these residuals and those linears. Okay. Now, if I'm looking at these and I'm looking at the first one, okay. So if I go, okay, A, which one does A look the closest to? 1, 2, or 3? Which one does it look like that residual fits that model? Now, with the residuals, we can't really tell anything about it being positive or negative if the slope of the linear line is positive or negative, because our goal is to have it kind of spread equally. And so looking at this, what we'd want to do is we'd want to see the spread. So if we look at A, which one looks like the one that matches A the best, which would in this case be number 1. Okay, A fits number 1 because you see all the data is fairly close to it. Okay, it looks like a straight line, all the data is close. That's what it is. Okay, so now take a second. What do you think B and C are going to, is B going to be with 2 or 3? Is C going to be with 2 or 3? So in this case, B is going to be with number 3, and C is going to be with number 2. Now, easy for C is because if you look at the data, it looks like A, but it's farther spread out. Okay, and if you look at 1 and 2, they look similar. It's just 2 is farther spread out. Okay, the data is kind of spread out more. It's not centralized around that line. 3, though, if you look at 3, you see that linear line, and then if you follow the data, and if you didn't want to follow it linear, you see you kind of get this little hump in it. Okay, and that residual plot exaggerates that hump. Okay, because we're just taking it based on what it is. So that hump is seen more in that residual plot than it would be in that linear model, because the linear model again wants to basically divide the data in half. It wants half the points on one side, half the points on the other to get it equal. Okay. All right, so the correlation coefficient, which is R. Okay, so the correlation coefficient, which is denoted as the letter R, measures the strength of a linear relationship. Okay, that number is always going to be between -1 and 1. Okay, the closer it is to -1 or 1, the better that graph fits. So if the number is 1, that means it's a perfect fit. If the number is -1, it means it's a perfect fit. If it's at 0, that means it's a weak fit. It probably isn't right. It doesn't really work. Okay. Now, the one thing nice with the correlation coefficient is the sign. So the sign tells you if it's positive or negative. So if you have a R of -0.5, that means it's decreasing. So if the R is -0.5, that means that your overall graph is going to be decreasing. If you have an R of 0.5, that means that it's going to be increasing. Okay, so the sign tells you if it's positive or negative with its slope, if it's increasing or decreasing. Okay. Okay, so here are a bunch of different ones, and you can see the R's change for all of them. So the first one we have like 0.33. That means it's a positive, so our line's probably going to be something like that. And you see it kind of is an okay fit. 0.69, it's a better fit. The numbers are closer together. 0.98, even better. And then you see the last one is 1, which is a perfect. And then the bottom is the negatives. So you see here it says R is -0.08. That means it's a very weak one, but the slope ends up being a negative in some way. So the slope's going to be falling in some way. But the data is so spread out that it doesn't fit very well. This one, negative, negative also, and the last one is a perfect fit at -1. Okay. So again, the R tells us how well it fits, and also tells us if it's a positive or negative number. Okay. This is the formula to find the correlation coefficient. So you have R is equal to 1 over n minus 1 of the summation of each residual being multiplied after they are divided by the number. So it's this whole thing. X bar, Y bar is the sample mean of the XY. SX, SY is the standard deviation of your X and Y. You subtract those, you multiply them. Each data point. So if you have 100 data points, you have to do this calculation 100 times. Find the sum of them all and then multiply them by 1 over 100 minus 1. So it's a huge mess. Okay, that you're going to have to do. Just kidding, you don't have to do it because you have calculators and computers that'll do it. This step-by-step is for TIs, so if you have an 83 or an 84, he would be a step-by-step for you. The first part is to help you find your R, because sometimes when you type in a regression, you won't get the R value. Okay, so this is for that. And then the rest of it is a step through, and it helps you find your linear regression. There's also quadratic regressions. There's a whole bunch of different regressions. So there's 2 different regressions. You just have to make sure that you pick, that you use the right variables. So one is AX plus B, the other one is A plus BX. So just make sure you pick, whichever one you pick, make sure you write the equation correctly. Okay. Right. So looking at some trends here, and the problem is that we might not see that they are linear. So if we look at these, we see that the first one looks more like a curve. It's not linear, but we still get an R. Second one looks like it kind of dips and then goes up, but we still have an R. Because even with data that doesn't fit something properly, we can still draw a linear line. This line is going to be slightly negative, this line is going to be positive, and this line is going to be positive as well. But as you see, the data kind of goes up and below it. Okay, so just because you can do a linear line doesn't mean, and you can get a strong linear line, doesn't mean that a linear is the best fit for those. Because each one of these, linear would not be the best fit. Okay. Okay, so here is our possum graph again. So what would change? Okay, what would change if we took this graph and we changed the y-axis and we changed it from millimeters to centimeters? Okay, the main thing is, yes, you would have some changes, but would the R change? So would the line change? Would the line change? The line would change because you're changing the x, the y's, but would the R change? So would that correlation coefficient change? So no, the R would not change. Even if we changed the x also, if we changed the unit on both, we wouldn't. As long as we keep the units consistent, okay, and we didn't change the actual data points, we can change these numbers, but we're still going to get an R. That line is still going to fit that data the same way. So if we change the units of the X and the Y, our R is not going to change. Because, I mean, millimeters, you just change those numbers to 850, 900, 950, or the bottom, the centimeters. You just add zeros to the end of each one, and you have the exact same graph. So you have the same graph, it's not going to change anything. The R is still the same. Okay, so the R is still the same even if you change the units on them. Okay, all right, that's it for this section. It was a long one. It was a lot of material. And we're going to keep looking at these regressions. Make sure you use calculators. You can always use a calculator to write the regression. You don't have to do them by hand.